All right, good afternoon, all. It's really good to stand up here and talk about some of the data we have. So just to clear the air a little bit, unlike a lot of people in this audience, for background, we are not actually building large-scale, high-capacity networks at scale, but we're pretty good at finding faults in them. And that's really what this talk is about. It's about some interesting events that we've seen in the past. And I wanted to share with the audience here, some of you might be affected by these as well, so it would be good to get some perspective on what you guys saw during these events as well. So just see if this works here. Real quick, before I get into the details of this, I wanted to spend a second just talking about the data set that we're working on here. So at a high level, this is a combination of two different kinds of data. So if you look at the first set of data, it's what we call as active probing. So this is where we use about 120, 130, 140 sites that are geographically dispersed to test performance at various layers, at the application layer, at the network layer, including the hop-by-hop paths, etc., from these sites to specific targets. So for example, we would be looking at connectivity and performance to Facebook, to Twitter, to Google, to all of the popular sites. And in addition to this, we also have the data that we collect from a bunch of our users. On the routing side, and this is where it gets a bit more interesting as well to this audience, we do ingest data from the BGP feeds, such as route views and RIPE. And what is interesting there is, again, correlating the BGP data with the layer 3 information that we have. So at a higher level, that's the data set that we're talking about for the rest of the talk. And I'll go through details as we come across them. So one of the things we noticed when we started collecting data and really looking at this data at a larger scale is that there are outages happening all the time. And if we cared about every single outage, then we would be busy all the time. We wouldn't get some sleep. So what we've seen is lots of outages going on all the time, but not every outage is affecting the vast majority. So what I'm going to focus on for the rest of the talk here is 3 outages that were fairly significant, fairly wide in terms of the impact, and we'll dive a little bit deeper into what happened there. So the 3 events that I mentioned, they start with the most recent being the DNS root server attack. How many folks were aware of this in the room? Just a show of hands, the DNS root server attack. So there was another one in December which got a lot of publicity and was much worse, and so I'm guessing there were more folks that were aware of that. The submarine cable fault, folks that were aware of this or were impacted by this? Anyone in the room? See a few hands. And then the AWS Route Leak. How many people were impacted by that or aware? Okay, good. So these are the 3 events, and they're 3 different, very different events. So we'll go into that one by one. I know I'm standing between you and a break, so I'm going to keep a good pace here to keep moving. So the DNS root DDoS attack. This happened on June 25th. It started at about 2:45 p.m. Pacific, about 21:45 UTC. It lasted for about 2 hours and change. Actually, 3 hours if I do the math there. And what we saw was really interesting is you saw the impact across all the root servers. So it's not just one root server or 2 root servers. It was impacting all the root servers. From what we know, this was a SYN and ICMP flood that came through. And the volumes were pretty high at about 15 to 17 gigs per second. So that's what we know about the attack. Now, what you see on the graph here is showing the availability of the root servers across all the servers. And you can see a dip. And then it's gradually starting to come together as people are starting to grapple with the attack, right? The other thing to keep in mind for this is just outside of the availability issues, we also saw a fairly noticeable change on the average response times. Now, this doesn't seem like a huge change. It's still 13 milliseconds averaged across all the different sites. But this is because a lot of the sites are anycasted. So they're pretty close to where the probing points are. And then this graph, which is really interesting, shows you the impact that was on each different root server. Now, what you notice here from the top to bottom, we've sorted it based on the number of errors we've seen, and the errors being the availability errors in this case. So we see H root server and B root server in particular taking a pretty big hit in availability. And then on the bottom end of the spectrum are the ones like A, J, and L that are doing fairly well compared to the volume of the attack and the disruption we saw across the rest of the root servers. So we thought this was really interesting that it's impacting different root servers differently. And there's a whole lot of factors that go into why this happens, but there's one particular pattern that we saw that I thought was really interesting and worth sharing. So if you look at the servers, again, we'll focus on this, but as a side note, just a similar behavior was also seen by the RIPE DNS MON data, where you can see in this very readable slide up there with all the large fonts that the red belongs to the B root servers, and then the G and the H, which are the same as the top three here. Now this, again, as I mentioned in the prelude, is not as bad as the December 2015 DDoS, just in terms of the impact, right? So that's a comparison point. Now we'll focus on the H root server and look at one thing that was interesting there is H is anycasted from 2 sites, and they're both in the US. So that's just one fact to keep in mind, and let's move on, we'll make some conclusions. B, which was the other one on the list at the top, which was impacted the worst, was also anycasted from, or actually it's unicast, it's not even an anycast site here. It's something to fix. So that was announced only from one site, right? So that's the B root server. Now we focus on the bottom end of the spectrum, the ones that were least impacted, and the J root server has had at that time 113 anycast sites. Now this picture was taken recently, and as of now they have 116 sites. So they have added 3 more sites since the DDoS attack, but the reason the title is 113 was at that point it had 113 anycast sites, and fairly well spread out internationally as well. And the L root server has 154 anycast sites. So if you notice, there's a pretty strong correlation here between the different impact that you saw at the highest level, where there were 1 or 2 or none in terms of anycast sites, to the lower end of the spectrum where they had a lot of sites. So we could clearly see a correlation between the number of sites and the impact on the attack, right? And it makes sense because anycast is basically regionalizing the attack to a large extent. So if you have attack traffic coming from South America and you have an instance there, it's taking the traffic locally if it is done right. So that makes sense. But we did see some interesting patterns where there were a few exceptions where some root servers had a handful of anycast sites, but they actually did pretty well. And when we looked into that, it seemed like the capacity was a big factor there, that they just had a lot of capacity and they could manage all of that. So that was interesting. And the key point I want to make here is just anycasting doesn't necessarily mean that you're going to suddenly be good against DDoS. You still have to work at capacity. So that's an interesting point. The other thing we noticed was during this attack, as the attack started, we saw root operators starting to make BGP changes. So this is one where it's the A root operator, and we see a lot of changes. Now, I'll just quickly go through the graph here so you can make some sense out of that. The green nodes up there, the ones that start with 36, they are the destination AS that is announcing the block for the particular route. And then the white nodes were the ones that were announcing it before that have now stopped announcing it. So you can see the route origination is shifting, the paths are shifting, they're trying to move some traffic around. And that was pretty consistent with other route operators as well. We saw a lot of other shifts similar to this where there were route changes going on as they were trying to handle the attack. The other thing to note was the layer 3. On layer 3, when we looked at just the packet loss metrics, looking at it hop by hop, this I believe is the H, which is with the US Department of Defense, and the loss was not only happening at the terminal site at the network which hosted the root server, but it was also happening upstream from the network. And this was just an indication of the volume of the traffic and the fact that the upstream ISPs were also to some extent struggling to deal with this. So that was an interesting observation as well. So this is just a quick summary of the things we find that are pretty common in some of these DDoS attacks. We find availability being hit. We find the resolution takes a good standard deviation different from what it was before. And in this case, for DNS in particular, you'll see multiple root servers impacted. It was not directed at a specific route. And then we saw an impact on the upstream as well. So that was the quick summary for the DDoS on the DNS servers. The next thing we look at is the SemiV4 a CVV4 cable fault. And this was, again, a different kind of event because it actually involves an undersea cable, which is a really hard thing to fix in a matter of seconds or minutes, right? So as an example, one of the things we saw in this particular event was this is a layer 3 trace going from one of our locations in New Delhi. And it's the fork point that you see where there are 3 red links. The red is not a problem there. The red is indicating high latency, and that actually is indicating that it's a long hop link between, in this case, Bombay and Marseille. So that's the link that exists between Bombay and Marseille in that case, and that's under normal situations. That's how the trace would look. Now, what we noticed for the same trace at that particular instance of time, around May 17th, around 6 Pacific, was that traffic was terminating at the Tata exit point in Bombay. And so, given that it was one end of the long hop link, we had some guess that this is something to do with a cable, and it's not necessarily a Tata issue. So we continued to look, and we also noticed that a similar issue was being seen in Telecom Italia, but in a different part of the network geographically, but it coincided with the similar time. So in case of TI Sparkle, we saw the issue being somewhere in Italy where packet loss had started, going from Romania. So 2 different providers being impacted by a very similar event at the same time. And then we noticed BGP changes as well. So this is one example where Netflix was directly peering with TI Sparkle. And that's the left-hand side of the picture here. And then on the right-hand side, you see the TI Sparkle Netflix BGP session is now no longer being advertised, but TI Sparkle uses level 3, 3356 to reach Netflix. And so what we saw was some quick reactions from some of these providers, such as Netflix, to try to get around the problem. So it's a good sign. And then we go down to just looking at what is common between TI Sparkle and Tata, and found that the SemiV3 and SemiV4 cable segments were shared by both of them. So this is, again, we're looking at this real time, so we don't really know what is going on. This is, at that point of time, it's our guess on what actually is happening, and we narrowed down to one of these 2 segments that were potentially problematic. So that's where we were at that point. And if you focus on the SemiV4 cable, that's the Southeast Asia, Middle East, and Western Europe. That's what the cable connects. That's some information on the cable. And it seemed like the impact definitely had impacted the connectivity to India, but also had impacted parts of Europe around Italy and so. Now, one other interesting thing we saw is at the same time that this was happening in the Europe and Asia region, we noticed something interesting. The traffic from Santiago in Chile was also not going anywhere, and there was some packet loss happening inside the Latin America continent, which was really weird, and it confused us a little bit on how has this got anything to do with our possible guess that's a cable event. So when we dug further, we found that in this case, TI Sparkle was actually routing via Miami and New Jersey to go connect the Europe's component with the Latin America component. And in addition, what was happening was right around the same time, we noticed a lot of BGP issues. This was data collected from the BGP peering data from TI Sparkle, and the issues were not local just to Europe. Now the issues were being seen for countries, including Argentina, where we saw some issues in reachability of different prefixes, different size prefixes. So that was pretty interesting to see the ripple effect go across Europe and Asia. And then finally, at some point, there was an acknowledgement on the SemiV outage, and the data that was put on the public forums was that the segment 4 was the fault, or segment 4 was the likely cause, which connects, I believe, Cairo to Marseille. And we actually noticed that the issue could likely be a smaller segment of that, which was between Palermo and Marseille. And we're not really sure which exact segment, but our data was suggesting a smaller segment potentially being the issue. So just a recap, when we talk about undersea cables and so on, we all know that it can cause major disruptions because these are not things you can fix easily. We generally see that when things like this happen, it's impacting multiple ISPs. We see a lot of BGP routing changes that are being done to get around some of these issues. But one other comment here, which we found very interesting, is a lot of people focus on packet loss. And one of the indicators that can often be an early indicator of something going wrong at the network layer is the jitter. And we found various situations in which jitter variances, if you catch them early, are almost early indicators of potential packet loss that is happening. So we thought that was really interesting, and some of the measurements we're doing now going forward is focusing on seeing if this is a phenomenon that applies across different kinds of events. So with that, I'm coming to the final event, and I'm moving through this quickly, so it's about 8 minutes or so per event. So this is an AWS Route Leak event, and we've seen route leaks and hijacks covered extensively at NANOG, so this is not new to this audience. But yet another event, so we'll go through this in detail. And then I know there's a talk later today as well. If you're interested in this, there's another talk later in the evening that also talks about BGP hijacks, which looks interesting. So that shows you AWS routes on a normal day. So at the center of that graph up there is the ASN for Amazon West, AWS, and then all the connectivity is the peering or the upstreams that Amazon is using. It's pretty aggressively peered, as you can see, and I'm sure there are others that we don't capture as well. So the usual suspects, NTT, TS, Sparkle, Telia, CenturyLink are all part of that peering ecosystem. Now, this is how traffic would look from one of our locations in Portland going to Amazon. Now, this is Amazon East, right? So it's just transiting the country. In this case, it's going through Hurricane Electric in Chicago and then handed off to AWS, who backhauls it on their backbone. So that's how this traffic flows from Oregon or Portland to AWS East. And now there was a period of time here. So before I get there, this is the ASN map in this case. So Amazon peering with Hurricane Electric, and then Hurricane, in this case, advertising to 46841 from where we're receiving a BGP feed. So I wanted to focus on this for a second. There is a grayed out section on the bottom, which I'll come to in the later half of the talk. But this is a typical BGP path that we see. The block in question for this particular event was /20, 54239, 16/20. So that's what life was when everything was good. And now, all of a sudden, what we saw was when we were looking at the network trace, traffic from Portland is terminating in Zurich, which was really weird because it's supposed to be going to the east coast of the United States, but instead it's going to Zurich. So the layer 3 path that we see is actually crossing a continent and terminating. Something clearly seemed wrong at that point of time. And as we looked into this a little bit further, we noticed some interesting things on the BGP side. So remember the block we talked about was a /20. And what we saw here was there were 2 new /21s for the same block that were being announced at that particular point of time. Highlighting again the way this graph lays out, the green node is 65021, which is a private AS number, again, the origin, which is originating that block. That block was announced to InnoField, which is 2000759, which then passed it on to Hurricane Electric, and Hurricane Electric managed to propagate it further. So this is what we saw at the BGP level, which was really interesting. So clearly there was something weird going on here. And if I summarize it in terms of a Mickey Mouse diagram, as some people often call this, as private ASN leaking a /21 block to Hurricane Electric, which was accepted and then passed forward. And what made this particularly worse was there wasn't a contention for a /20 by 3 different providers. It was actually a more specific block. And that made it a lot worse from the standpoint of impact. This was, though, not as global as some of the other hijacks because from what we could tell, it was primarily through this particular path that it created some disturbance. And then when we looked at the actual incident and the explanation that was given, it turned out that it was an accidental leak that happened and was passed on to HE, which eventually passed it on to its peers or customers. We've got some indication that it was a route optimizer issue that didn't work out as per plan, but we don't have confirmed data on what exactly happened and why that occurred the way it did. And again, this is very similar to another incident that happened with Enzu in 2015, which you might be familiar with as well. So route indications, again, route leak indications, and we've talked about this at NANOG quite a lot. So there's a few different things to look out for. You suddenly see a new prefix, which is more specific. That's usually a sign that there's something weird going on, or a new destination AS, both of which were seen in this case. You also often notice major BGP route changes. And when I say major, it means the BGP path significantly changes. You all of a sudden see these new AS numbers in your path, which you've never seen before. And that's usually a good indication that something is very different. And then geolocation is another interesting thing. So in this case, you can notice that InnoField was a Swiss exchange in the BGP path, but also you noticed on the layer 3 traces that there was packet loss at a geography which was not really part of, or supposed to be part of your path. Didn't make any sense. So that's also another indication of a route leak. So just as a summary, we covered 3 events today. One was a DDoS attack, which was not really some fault in the infrastructure as much as just stress on the infrastructure. And we saw that Anycast made a big difference from what we could tell. Capacity also mattered. So Anycast and capacity as a combination, if you do it right, is a good way to deal with some of that. We talked about the submarine cable fault event, which impacted a few different regions, India, Asia broader, India in particular, parts of Western Europe, as well as Latin America. And then finally, the route leak, which this is one of the ones that I always find very interesting, because when you have a route leak, you can never predict what's going to happen. It really depends on how BGP picks it up and how it's propagated. So that's it. We do have a few more outages that we blog about, and if you're interested in that, I would advise you to go to this site. And if you have any questions, happy to answer. Either find me after the event or come up to the mic.
Hello, Mohat. Thanks for your presentation. My name is Doug Midori from Dyn, and I've written quite a bit about submarine cable cuts over the years, including a cut that when SemiV4 suffered a cut in March 2013. And these incidents are pretty major, and there's widespread, downstream impact. In this particular case in May, I'm not aware of, besides the outages reference that you cited from the outages list about a repeater being repaired over an 8-day period, of any reports of SemiV4 experiencing a cut or a fault. Did you guys reach out to any cable operators or telecoms to confirm that conclusion from your data?
So just to repeat the question, if people have, hasn't been a very well understood or well accepted public explanation of what happened. Is that accurate, right? And so to answer your question, I do think there was some reach outs. I'm not really sure about what specific cable operators were contacted and whether they got a response. But from what I could tell, the team had told me that there wasn't any private acknowledgement outside of what was public on what the event or the impact was.
Okay.
So, but if there's anybody in the audience who knows something that we don't, then you can add it. Right, any other questions? Thanks all. Thanks.